Hey everyone, welcome to The Explainer. If you live in the Midwest, you absolutely know the drill, right? The snow starts melting, a rainstorm rolls in, and suddenly, boom, your street is a literal lake. Well, we're going to skip the usual agenda today and just jump right into this very specific, kind of messy Midwest mystery. Why does the drainage system just completely fail under these exact conditions? Let's unpack the source data and see what's actually happening underground when rain meets snowmelt.
Okay, Section 1, the drain backup mystery.
Okay, let's dive into this. It's a question that has probably crossed your mind while you're just staring out at a flooded intersection. Like, why does a moderate spring rain seem to cause so much more chaos than a massive summer thunderstorm? The answer actually lies in this sort of perfect storm scenario where timing is literally everything.
The real secret here, it isn't just about the total volume of the rainfall or the snowmelt. It is entirely about velocity. You see, during these rain-on-snow events, massive amounts of water surge from the compacted ground straight into the drains in a matter of mere hours, not days. And well, the system simply isn't designed to swallow that much water at that speed. It's like trying to drink from a fire hose.
Moving on to Section 2, fast runoff and frozen ground.
And this brilliantly illustrates the core difference. Think about a typical summer runoff event. The soil is soft, it's permeable, which allows for natural infiltration that basically sponges up a huge portion of the water. But early in the spring, the ground is still completely, or at least partially, frozen solid. This frozen soil acts like a concrete slab, a totally impermeable layer which drastically reduces absorption and forces almost all of that water to run off rapidly across the surface, beelining straight toward the drains.
Now, the source material highlights a really critical detail here. Thawing and refreezing cycles can leave ice in gutters, inlets, and low spots. So, even as ambient temperatures start to rise, those stubborn blocks of ice, they remain lodged exactly where the water needs to go. This severely limits the intake capacity right at the source. It's like having a traffic jam right at the on-ramp.
Let's move to Section 3, the overlapping peak problem, and see how this all builds together.
So an overlapping peak happens when snowmelt front-loads the system. Naturally, snowmelt accelerates during a warmer stretch of weather, but when that warming coincides directly with an incoming rainstorm, the drainage network experiences this overlapping, combined peak. You know, the system might easily handle a rainstorm by itself or the melting snow by itself, but when those two peaks overlap, the flow is pushed entirely beyond capacity. 2. That is the magic, terrible number we're dealing with here. We've got two separate, massive water sources surging at the exact same time. The meltwater adds this huge surge directly on top of the rainfall. And this double teaming effect is incredibly harsh, especially in older neighborhoods, where the underground infrastructure just wasn't built to modern, high-capacity standards.
Which brings us to Section 4, bottlenecks in the system.
Look, storm drains have strict physical limits based on pipe diameter and pump capability, for sure, but real-world hydraulic capacity is drastically reduced by what we call capacity limiters. Just imagine the municipal drainage network being choked by debris in the inlets, leftover sediment buildup, vegetation, street trash, and, of course, ice or partially frozen material. With all that junk in the way, the functional diameter of the pipe effectively shrinks. So the crucial point is, because water inevitably seeks the lowest point, when those inlets are bottlenecked, low-lying streets suddenly become unintended channels. They essentially transform into localized temporary rivers, sending all that excess water toward the exact same constrained drainage points, and that aggressively increases the likelihood of localized backups. It's just a giant funnel that's clogged at the very bottom.
All right, Section 5, combined versus storm-only drains.
Now, what's really interesting about this slide is how the consequences of a backup depend entirely on mid-century civil engineering. In older areas that utilize combined sewer systems, stormwater and wastewater actually share the exact same pipe network. When overwhelmed, this can lead to unsanitary wastewater backing up directly into homes. Gross, right? But in modern storm-only systems, the pipes are entirely separate. A failure here generally means manholes and culverts hit their constraints, causing really aggressive surface flooding. Residents actually often misinterpret this street pooling as a pipe backup, even though technically it's a downstream constraint.
Now for our final piece of the puzzle, Section 6, spotting the warning signs.
You can actually witness a storm drain hitting its breaking point, and it's quite the process. It starts visually, right, with water pooling excessively around curb inlets as the intake gets clogged. Then it becomes auditory. You'll hear these strange gurgling sounds from the drains, which signals air struggling against a literal wall of water. As the system reaches maximum capacity, runoff from streets and yards noticeably slows down, and eventually you'll see rising water near the outfalls. When officials are out monitoring these escalating signs, they know for a fact the system is redlining.
So, as we wrap up this explainer, we have to ask a really tough question. Knowing that timing and peak flow matter just as much as volume, how can communities actually better plan responses and long-term drainage improvements? The mix of heavy rain and snowmelt compresses all that runoff into a tiny, super destructive window. The real challenge here is figuring out how to adapt our aging infrastructure for the overlapping peaks of tomorrow. Keep an eye on those curb inlets next spring, everyone. Thanks for tuning in, and we'll catch you in the next explainer.